All right. Yeah. So thank you, Ju. I was hoping to speak today about really how my own perspective on CO2 capture has evolved in the last couple of years. And it's kind of gone from viewing the capture step and the upgrade step as distinct to viewing them in a kind of integrated fashion. And I'll talk a bit about how that's brought us some new ideas. But first, I will start with the IEA roadmap that Ju already alluded to. Clearly, we have a big project in front of us in a world in which economic growth and potentially total CO2 emissions can actually grow, and we need to shrink them. We need to combine, obviously, behavioral modifications and avoided demand. We need to increase energy efficiency. We do need to grow the hydrogen economy, and there's a huge opportunity to electrify as many processes as we can. Having acknowledged that, there are some things that will be difficult to abate, some sources of CO2 that will be difficult to abate. And so carbon capture and sequestration, and I would add carbon capture and utilization, when the utilization takes the form of materials that effectively sequester the CO2 for hundreds to thousands of years, are also a very significant interest. And the particular interest in utilization, where we're not just avoiding net emissions, but we're actually adding market value to products that lever the carbon and CO2, creates, if we do it right, once we get the techno-economics right and we get the CO2 footprint right, it creates a positive economic force towards our climactic goals as well. And as we think about the decarbonization of the chemical sector, which is something that I'm particularly interested in, we can break it down into really a couple of stages in what I'll call progressive decarbonization. Now, clearly, because there's a significant CO2 footprint associated with the energy needed in CO2 reduction, CO2 processing, and in general, fossil fuels, chemical manipulation, there's a chance to electrify some of those processes to avoid the emissions associated with the energy that's currently being provided by fossil feedstocks. And so an example of this would be electrified steam cracking. And it has significant decarbonization potential, and I think it's going to come soon. But it's also important to acknowledge that there are limits to how much of our CO2 footprint this can address. It's perhaps roughly in the third to half range, depending on the specific process that we're looking at. And so you can view what I'll talk quite a bit about today in the form of feedstock substitution as a significant next step that gets at a very large portion of the remaining CO2 footprint. And that is the idea to replace fossil feedstocks with CO2. So for example, if you in the short run do, say, capture from a point source, and in the longer run do direct air capture, and then you utilize that CO2 and reduce it using green electricity, so low carbon electricity, to the molecules that make it into the materials of our lives. Ethylene is one good example. Then you have the potential to add further decarbonization prospects. I'll be talking about really some R&D because this is work that's going on in the research labs of academic institutions today, and is less far along than direct electrification is. And then I'll also talk a bit about how this is my section 3 called intermediary chemicals, how there's a significant carbon footprint associated with further processing molecules down the value chain. So just to give one example, propylene to propylene glycol, that step itself, and that's the fate of a significant amount of propylene, that step itself has a significant carbon footprint owing to incomplete selectivity, where there's some CO2 emitted in the process, and there's also some process energy. And so we've been starting to spot specific opportunities to contribute to decarbonization around this petrochemical processing a little bit down the chain. So I had always kind of viewed CO2 capture and upgrade as kind of occurring in two distinct phases. So you'll see here I've got a point source on the left, and I can do flue gas capture in order to provide a concentrated stream of CO2. And that CO2 using green electricity and water can then be electrically upgraded to chemicals and also to fuels. But looking at the right loop, and the right is a loop now, there's the opportunity when we utilize emissions that can ultimately be captured from air using direct air capture to produce CO2 streams, or to generate concentrated CO2 streams that can be utilized by electrochemical systems that actually originate from ocean capture or air capture. And then from a cradle to gate perspective, these are the ones that have the opportunity, given the direct air capture approach, to contribute in a carbon negative direction. Now, what's captured my attention recently, and this is the kind of integrated word in the title of my talk today, is that we might find benefits, economic and also total energetic benefits, from integrating the capture and the upgrade process. And so I'll try to compare and contrast a bit the kind of currently envisioned approach, which runs along the top of my slide, and then to tee up what I'll be talking about for the first section of my talk, which is the integrated approach. So the current approach would be to utilize, in direct air capture, for example, to utilize a contactor to contact CO2 to either a liquid, amines, and what are called advanced amines, sort of next generation amines, and also carbonates are famous examples. And then solid sorbents have also seen great progress recently, which use some of the same functional groups, but tethered onto a solid support. And then the first step here is then, once the capture's occurred, to re-emit the CO2 that's been captured into the liquids or onto the solids, to do it often with a thermal swing or a pressure or vacuum swing, and then to produce this concentrated stream of CO2 that I was talking about on the previous slide. And then in a second stage, in a distinct stage, to use a gas-fed electrolyzer that takes this concentrated gas-fed CO2 and takes it ideally all the way to something that's been upgraded. So CO would be an example. Carbon monoxide, not necessarily as the endpoint, but as a very nice feed to the ensuing further upgrade stages. Now, this, of course, then produces the lean sorbent, or it produces the solid sorbent that's been denuded of its CO2. But what we've been looking at is whether we could instead take the liquid, in the case of these liquid capture solutions, or just as much in the case of the solid sorbents, take the solid sorbent with its CO2 bound, and then directly feed that concentrated adsorbed bound CO2 into some form of electrolyzer that would then take it towards something more valuable, such as CO or syngas, or better yet, say ethylene or propylene. And this, of course, would then have the same final effect of having stripped the CO2 from the solid or the liquid sorbent, which could then, of course, then be recycled. So just to give you a bit of an engineering cross-section of what a system like this would look like, there's a CO2 capture phase that interacts, for example, with the amine. Now the amine is rich with CO2. Carbamate, for example, the adduct of CO2 in the amine is now provided. And then we flow this liquid directly into our electrolyzer and build an electrochemical cell that's capable of ideally producing CO with very high purity, and ideally it will be with very high energy efficiency as well, because our chief cost in these systems will be energy for at least the foreseeable future, even as electricity prices hopefully come down for green electricity. So in one of our works on this subject, we worked with amines. Now, amines, I need to acknowledge, are traditionally used in point source capture, so flue gas capture, for example, and they're not traditionally used, at least in the liquid form, in direct air capture. So for from the viewpoint of direct air capture, think of this as a bit more of a model system, and one where we would need to move to advanced amines or amino acids or some other options for liquid capture systems. And what we found actually when we attempted this in one of those electrochemical cells that I described is that actually it didn't work very well, but we understood why, which is we realized that we actually had the amine molecules blocking the interaction between the carbamate to which the CO2 was bound and the catalyst. And so we weren't really able to electrochemically access because of this blocking layer. But when we introduced a high concentration of cations, so for example, when we introduced a potassium-containing electrolyte into this system, then we were able to have this very thin cation layer and to interact directly with the CO2 bound as carbamate with the amines. And all of a sudden, the system really turned on. And we were able to produce CO at about a 70% Faradaic efficiency. The rest was hydrogen, so you could call it a blend of syngas, although I think probably the most interesting thing for the future of this project would be to continue to increase the CO purity and think of having a separate source, like a water splitting electrolyzer as the source of green hydrogen, if syngas is what you want. This, of course, we then cycle. This is showing a 10 cycles each 10 hours, showing that we could reutilize the amines that were in this system. One of the advantages of this approach is that because it didn't rely on temperature swing, it didn't go to the temperatures at which the amines are particularly vulnerable to flying away since they're volatile. And so we were able to operate at a modest 60 degrees C temperature in this work. And as a result, the cycling is good. Now, a more famous direct air capture liquid is the carbonate approach that I mentioned. And so in the carbonate system that we worked on recently, we instead utilized a bipolar membrane to produce protons that would react with the carbonate to produce CO2 that we could then interact with at a separate catalyst that was distinct from the left edge of the bipolar membrane. And so this too was a means to produce syngas. It produced about a 2-to-1 syngas ratio, the ratio of CO to hydrogen, and allowed us in this system to get an overall energy efficiency, looking at the total syngas production, of about 35%. That leaves some room to improve. We'd like to get to 60 or 70% full cell efficiency. And the main opportunity is in reducing the voltage that was required to drive this. And some really exciting recent advances in the understanding of how bipolar membranes work, I think, could help us move significantly in the direction of reducing the overall voltage costs and therefore increasing the overall energy efficiency of directly producing syngas from capture liquids. This too we ran now in a cycle and showed that over a 150-hour operating time, we were able to produce a range of syngas compositions, something that we were able to tune by the operating conditions of the system. So you can see now that we can have CO2 or CO, i.e. having undergone a first upgrade step known as reactive capture. It's one of the keywords that we use, the community uses to describe that work. And so now we can kind of launch off and think about more valuable chemical products that we can create. Now, when we do either CO2 or CO electrolysis, we're faced with a very rich palette of possible chemical products. So amongst the C1 products, we can produce methane, methanol, etc., formate. Amongst C2 products, we can produce ethylene and ethanol, and you can imagine that we get a richer network of possibilities as we go to larger and larger carbon numbers. And so selectivity ends up being one of the first really interesting challenges in these systems because the purification costs will be too high if we don't produce substantially a single desired, saleable, substantially pure chemical product. So we need to see how we can target selectivity. And that's measured in these electrochemical systems from the Faradaic efficiency. This is the fraction of the electrons that are utilized in the system and that go towards producing the desired product, whatever it is. So you see on the right, my orange bar, that PEM electrolyzers, so the ones that are used in the production of hydrogen, are perfect on this front, or as close to perfect as one can be, and they just produce the desired hydrogen product. In some of the work I'll talk about today, we've gotten to about 80% in the Faradaic efficiency to ethylene, but we'd like to keep going from there. And the reason is to minimize these separation costs as much as possible. And of course, it also contributes to the overall energy efficiency But I think the bigger issue actually is avoiding the separation or minimizing the separation costs. The intensity is another critical metric. The capital cost of these systems will only become acceptable once we reach an intensity of about 1 amp per square centimeter. Now, in the last couple of years, the community has increased the ethylene productivity in these systems to about 1 amp. And so that's looking promising. But as always with these things, when you sort of break it down into these separate axes, you then realize you need it all to be combined simultaneously in one set of operating conditions. So you need this Faraday efficiency accompanied by this partial current density, accompanied by this energy efficiency and lifetime. And so it's really getting all of these simultaneously that is what we will be judging ourselves upon. The energy efficiency is very much the kind of bottom line here. And ethylene efficiencies towards the production of ethylene have actually now risen a bit above 20% using a tandem approach based on CO2 to CO, followed by CO to ethylene. But it still leaves us a ways away from our target of getting to a 60% energy efficiency. This is based on techno-economics. It assumes still a fairly low price for green electrons down the road. So for example, if we use 3 or 4 cents per kilowatt hour, we still believe that we'll need to get the efficiencies up in a fairly significant way towards these kinds of numbers. And then there have been early runs on efficiency with hundreds of hours. This is just a kind of publishing norm within the academic community. We're going to be going after 10,000 and 100,000 hours for these systems ultimately. Now, thankfully, there are many degrees of freedom in material science and materials chemistry that we can use to control the catalysts and to vary the catalysts in order to strive for selectivity and productivity and energy efficiency. We have access to nanostructured catalysts and nanostructured supports, and we have access to support effects where the nature of the material on which the catalyst is adsorbed in turn influences the catalyst's performance. We have, through nanotechnology, access to shape through vertices and edges of crystal facets. And we have the possibility to confine certain reaction intermediates between, say, catalysts and overlayers. And we have heterostructures at our disposal. Of course, we can make alloys, we can make high entropy alloys that include many elements, but we can also make heterostructures that envelop them within a shell, and where the inner core actually influences the behavior of the shell catalyst. So we have many degrees of freedom. What I think still needs development is the rational understanding of, first, how we implement these specific materials compositions, second, how we ensure that they are operando stable, so they will reconstruct. So we need to design for the catalyst that we want under its operating conditions of electrolyte and applied potential, rather than for the pre-catalyst that we put into the system. And finally, we need to be able to design rationally towards performance. We need to understand the relationship between the structure and the function that I've described here. So in our group, we were, over the last couple of years, working very actively in this area, and we developed a kind of platform system that was a gas phase electrode. You see here a GDE, a gas diffusion electrode that can bring in the CO2 ingredients. It can allow us to extract the gas phase ethylene. It utilized a thin catalyst layer. These were copper nanoparticles in these initial studies. And this in turn was interacting with an electrolyte and actually had an electrical contact on top that was something that the electrolyte was able to penetrate through. And so what we had formed here was a gas, solid, liquid structure where those three phases were able to meet along a rather well-defined, even at the kind of tens of nanometer nanoscale, a well-defined plane. And this led us to an initial baseline just using copper of about a slightly under 70% Faraday efficiency ethylene producing system that was able to sustain that operation for the course of about 150 hours. And so with this platform, we were then able to ask, when we start to tune and alter these catalysts beyond copper alone, what can we accomplish? So I'll just give a little taste of one effort in that regard. We were interested to explore how the ways in which CO adsorbs on a catalyst influences the coupling. Of course, we need these CO intermediates to interact with one another to form a C2 product. And what we found through initial computational studies is that the motif by which the CO was bound on the copper catalyst influenced the energy barrier associated with this coupling. And then we could lower the barrier if of these two adsorption motifs, the atop and the bridge, if we could have the two in fairly equal proportion so that there were a fair number of atop-bound CO intermediates that were neighbors to a bridge bound and could therefore participate more readily in coupling. And what we realized is that this was something we could potentially influence with small molecules in close proximity with the catalyst, and in particular that N-aryl pyridinium salts were ones that we could use to control the ratio amongst these two binding motifs on the catalyst. So this led us to partner with these co-authors you see up here, Teo Agapi and Jonas Peters, who are experts in everything, I mean, in electrocatalysis, but also in the design and synthesis of these kinds of molecules that allow the regulation of electrocatalytic properties, and in this case of these adsorption sites. They were able to generate a library of N-aryl pyridinium salts that they were able to screen systematically, and were able to look for how the choice of adsorbed molecule was influencing the atop to bridge ratio of the CO intermediate adsorbates. And then, of course, when we built systems, we were able to measure how that influenced the ethylene Faraday efficiency. We were able to link that with the Bader charge on the nitrogen-containing group and build what essentially amounted to experimental volcano plots showing the value in this approach to tuning the adsorbates. Then working again with exactly that team, we're able to electroligomerize the most promising member of this library and achieve in neutral media conditions, which are attractive for minimizing a challenge in CO2 reduction systems involving carbonate formation. We're able to operate in neutral media conditions above 70% Faraday efficiency, and also sustain this operation over 190 hours of continuous and consistent operation at an interesting current density, so an interesting productivity and an interesting Faraday efficiency. So this kind of led us to think, what else could we make? What would be something that would kind of push the frontiers of what electrocatalysis can do? And for this, we pursued the synthesis, this is quite recent work now, of higher carbon, so 3 carbon molecules in this case. And you'll note that this work is from carbon monoxide. So this both avoids problems associated with carbonate, and it levers the CO that we're now able to produce from the reactive capture systems that I talked about in the first chapter of the talk. Now we realized that our design principle now would have to get a little more sophisticated. We weren't just doing C1 coupling, though we would also need to do C1, C2 coupling. And so we needed to think about the design of catalysts. We probably need to bring in more degrees of freedom. So we worked with ternaries that would allow us to achieve simultaneously efficient C1 coupling and also C1, C2. And found some compositions that we were able to synthesize and, of course, compare to controls. And in this work, we're able to achieve a Faraday efficiency to N-propanol, a C3 molecule, of 37% at a good productivity, still leaves a little room to improve. And interestingly, we're able to synthesize really a preponderance of multi-carbon products. There was very little C1 left in the system, but it was a mix of C2 and C3, ethanol and ethylene especially, in addition to, of course, the propanol that was our intended target. Built a mildly scaled pilot, so scaled up from 5 to 15 square centimeter, and showed that when we did that and operated a system at 4 amps, we were able to keep all of those performance metrics that I described, and also increase a good utilization or achieve a good utilization of the CO. So achieve a single pass CO conversion. So, the fraction of CO that comes in and that ends up being consumed and converted into the desired coupled products. It's about 85%. That's good from a separation perspective, because then you don't have a really complex kind of recycle of your input CO. Now, the work on propanol, because of the high market value of propanol, work on propanol actually gets us closer to techno-economic viability than many of the other products that we've been looking at. We need to account for the dominant costs here, which are the CO input, which you could produce electrically, but we charge ourselves for it per ton in this analysis. The electricity costs, which are very significant. And there's still significant liquid separation costs here when you're trying to separate propanol and ethanol from one another. And achieved a projected plant gate levelized costs that is a little bit below the total sum of the existing market reference prices of the products that we would sell in the system. So encouraging in the sense of moving in the direction, or achieving a projected techno-economic positivity, but not with huge margins. And so clearly leaving room to improve further on the overall energy efficiency. This liquid separation cost can be improved if we increase purity, of course, of a single product, but it can also be improved when we produce our products at high concentration. And so that's another target for this field is high product concentration. These, as in other works, we showed how they achieved an operating stability of about 100 hours. And then in terms of where this could head, I think we'd love to go beyond C3. There's so many different chemical products of all the molecular weights that you could imagine that we'd like to be able to produce. And so going to C4 and beyond are interesting and challenging frontier topics for the field of electrochemical fuels and chemicals production. And I realize I'm getting a little light on time. So I think what I'll do is I'll be a little brief in this last technical chapter, because I want to give myself time to talk a bit about the roadmap for the field as I imagine it. This last chapter is about coupled electrolysis, where we produce one product on the cathode. An example is green hydrogen, and that could go along to ammonia production. And then we also decarbonize the production, the selective production of a oxidized product, such as ethylene oxide or propylene glycol on the anodic side. And hence the coupled electrolysis. We're doing two things and producing two things of significant market value, one on each side. And so the opportunity here is the decarbonization potential compared to only doing the water electrolysis is increased by also decarbonizing a desired hydrocarbon to oxygenate reaction. We got into this business a few years ago, realizing that to achieve high activities in these systems, we'd really need to find a better way than what we were being limited by in heterogeneous catalysis. And so we built a redox mediated system using a chlorohydrin route that got us to much higher productivities. These are the 1 amp kind of thresholds that I was talking about earlier, got us out into this regime where a lot of the prior work in this interesting, in this field, while promising, had been limited to rather low current densities that would be hard to translate into a low capital cost system. And then more recently have striven to build the full integrated system to go all the way from CO2 via ethylene to ethylene oxide, which is something that we reported recently. And so this, again, has a significant potential to, through these coupled electrolyzer technologies, achieve a greater degree of decarbonization, obviously, than either one would alone, and to contribute to multiple chemical transformations within the chemicals sector that currently have significant carbon footprints and that have large and even growing market demands in many cases. So yeah, I wanted to just say a bit more about how I see the field moving forward. One interesting frontier area for sure is scale. Our experience is that in seeking to scale from the gram per day lab scale to the small pilot that we built at about 100 kilograms per day ethylene production, that in seeking to provide that scale, there were huge challenges that we had not even sort of thought through. You don't think these through in pencil and paper, you think them through when a brilliant team of doctoral students and postdocs put their hard hats on and tried to build build this thing. And that's exactly what they did. And so there were all sorts of practical learnings to do with scaling the cell area, stacking the cells, dealing with heat, dealing with the reagents and the products, and trying to operate the system as we did for 30 days continuously. So a lot of insight to be gained just by doing. And we think there's more interesting work to be done there, including as we continue to refine the underlying catalysts and systems that we're building and translate those into these initial pilot scales. Another area that I think is one for real opportunity in this field and for others as well is accelerating materials discovery. This catalyst space, as I described, it's so large, and to search it just through sort of trial and error will simply take too long, and we don't have much time. We are in a hurry to advance some of these technologies and to get their performance up and their reliability up. And so an approach that we and other groups are taking is to start with simulation, but instead of doing all the simulation using, let's say, density functional theory, which is quite computationally expensive, do a curated set of simulations, but then train a machine learning model that can then explore, once trained, a larger chemical space. Use that as the basis to down select the compounds we wish to synthesize, but here too, add throughput, say through automated synthesis, and challengingly, through high throughput characterization. Here we need to find the proxies, the surrogates, for what will be a good catalyst or a good battery material or a good solar cell material. And so bring AI into the loop and feedback with its aid. As you can tell, we take a very metric-driven approach, and for all of these different chemical products, since the market prices vary, and this, of course, is hard to project how they vary relative to one another down the road, but we have some different targets for techno-economic positivity for the different products that we pursue. Some more challenging than others. Others, some made a little bit easier to get to techno-economic positivity by the significant market prices they command today, often a consequence of the difficulty in producing some of these chemicals through traditional thermocatalytic routes. We have a bit of a roadmap for how we move these electrolyzers forward. You can see that over the coming couple of years, we want to get into new regimes of energy efficiency, new regimes of operating stability, and really accurate theoretical predictability. But I wanted to end with a few thoughts that really aren't from me at all, but they're from the collective intelligence of my research group. We've been doing a group strategic planning exercise recently where we've asked, where do we want to go in the coming 5 and 10 years? And so this is a sample of some of the areas we want to go, and in a way I've been speaking of some of them, although this idea of direct capture and upgraded from dilute CO2 sources is very interesting. It goes beyond just the reactive capture I mentioned, but it also involves thinking about using a somewhat dilute CO2 sources, such as an ethanol plant's CO2 emissions or a steel plant's CO2 emissions, and utilizing that CO2 directly without further processing inside a next generation version of one of these electrolyzers. I mentioned coupled electrosynthesis already. There's a lot of really important work to be done on making green hydrogen more economically compelling. And a lot of this is on the design of better catalysts on the oxygen evolving side, or in producing more valuable products, such as I discussed under the coupled electrolysis. And I'll mention also that I think there's further work to do to make renewable electricity even more cost effective and even more scaled, that are very relevant to this community as well. And then there are many scientific questions that are frankly unanswered and that need to be investigated in depth. These are just a sample, but given that we are really building upon a legacy of 100 years of thermocatalysis and a huge amount of deep knowledge and learning that's been achieved, and given that there may be the chance to make tandem systems that unite thermocatalytic steps and electrocatalytic steps, how do we bring these together? Exactly the same question can be asked about biomass and biocatalysis. And to drive this rational approach that I described, we really need to understand the entirety of the material synthesis process. And we need to be able to then invert it. We need to be able to reverse engineer into synthesis of materials for function. This field is going to move a lot faster when we have better elaborated mechanistic pictures of how electrosynthesis proceeds. And computational studies are helping us a great deal to the extent that they can be further increased in their fidelity, and they can allow us to really pinpoint compositions that we can synthesize using SQ3 that truly do lead to predictively to the outcomes, to the performance that we intend. That will be very impactful. So I hope I've left lots of time for questions and discussion with this esteemed group. I did want to thank the sponsors of the work, and I wanted to thank all the people that did the work that I spoke about today, and to thank you for engaging today.
Thank you, Ted, for that very exciting talk. Ray just reported we have 6,000 viewers on different broadcasting platforms. We actually have plenty of time. So I encourage the audience to type in the questions in the chat box, and also for the panelists. So we have 14 on the panel. Just feel free to turn on your camera and raise your hand, either physical hand or virtual hand is okay. I'll maybe start by asking, firstly, in the you mentioned the thermal catalysis and electrocatalysis. So I think one of the trade-off often is, when you raise temperature, you may coarsen your nanostructure. So you could have an impact on the stability of the catalyst. So how much have you explored, let's say, beyond room temperature? What kind of temperature range have you looked at with your electrosynthesis approach?
Yeah, thanks, Ju. So most of the catalysis that I've been describing in our group today is occurring at or below 60 degrees. I think potentially when we're integrating it into systems that are really scaled, we could almost invariably be at 80 or 100 degrees C. And under those conditions, we continue to maintain our selectivity consistently, and we don't add, if you like, sort of new challenges beyond the fact that under the electrochemical conditions themselves, even at room temperature, these are dynamic catalysts that are evolving in the presence of the electrolyte and in the presence of the reducing potential that they're being operated under. But that's something that we study very regularly using operando techniques. However, I actually think it would be very interesting for us to be able to increase further in temperature. Obviously, kinetics become more favorable as we operate at higher operating temperatures. To operate at 100 or 150 or 200 degrees C with the heat coming from waste heat is very plausible and could be done without, really any significant impact in the carbon footprint of chemicals production. And so to the extent that temperature could actually be our friend here, and could allow us to increase intensity, I think that's an interesting degree of freedom that hasn't been fully explored yet in these lower temperature catalysis designs. And so to your question, I think we don't yet fully understand what will be the effect of that temperature when we creep up the temperature. The same comment could apply to pressure, by the way, not going to, mega pascals, but just operating at, 10 or 20 bar. Is something that could be very feasible and could potentially add productivity, could be a new degree of freedom and selectivity, but we will absolutely need to keep our eye, as you suggest, onto whether it impacts the state and the composition of the catalyst in ways that we need to anticipate and build into our designs.
Thank you. Professor Sarah Jordan has a question. What are the highest priorities for innovation? I guess that depends on the timeline. So maybe I can modify that question. What do you see is the highest priority, in the next, what would come online the fastest in sort of A+B speak?
Yeah. Well, there's a few questions buried in there. Sarah's original question, then Ju's added a nice one. Maybe I'll start with what I interpreted Sarah's to be, which is sort of like the attributes themselves. What are the attributes of these systems that we haven't yet fully knocked down? And she offered stability as a possibility. And it's certainly on the list. I would actually still say, though, that for this community, overall energy efficiency, and I have in mind here, of course, the electrical power associated with the electroreduction of the CO2 or the CO2 product, But in different systems, we have different separation problems. I mean, in all of them, we have either CO2 or CO at the outlet separation problem if we're producing gas phase products. When we work with liquid products, actually that separation of the CO2 or the CO at the outlet is mitigated, which is an attractive thing about the liquid products. But then we have to think about the energy of separation of the liquid products. And so I would say that, yeah, the overall energy efficiency, taking full account of providing the CO2 or the CO in a form that can be utilized by the system, then the energy of the box itself, and then the separation costs, that still has to be our number one priority until we've substantially fulfilled it. Because in all of our models, the operating cost related to the green electricity to drive those processes is still going to be the largest single cost. Having said that, I also agree that stability is another prime area. I think we are investing in that, but maybe 20% of our effort or so is invested in that. And I think we'll probably stay 80-20 on energy efficiency ratio to stability until we make a significant further progress there. I took Ju's add-on to Sarah's question to be a bit around the lines of, what would be a good go-to-market strategy, or what would be the attributes of a chemical product that could allow us to do A plus B? This is B, but it's sort of an early B. What could really allow us to bring new technologies on board swiftly? And I think it is chemical products that unite a very bad carbon footprint today. And so we and our industry partners to be very motivated, and that actually have promising techno-economics. And those often go together because, as I mentioned, the ones with the bad carbon footprints often have bad carbon footprints because the existing routes to produce these chemicals have multiple steps. Each step is not perfectly selective. So they add up to significant CO2 emissions, and they add cost. And so, I mentioned and propanol is one example of that. And it's certainly one of those processes that has a multi-step route, a significant CO2 footprint per step, and correspondingly a fairly high market price, just given the production costs per ton. Now, on its own, will that solve all the world's problems in terms of CO2 emissions? No, it's a couple $2 billion market. But I think in general, now looking beyond just energy, startups and companies looking for go-to-market strategies that first look at a really promising target that allows us to do some initial scale and to fund it through a really profitable target, that can be a good approach as we then try to tackle the really big problem on the gigaton CO2 scale.
Yeah, Ted, you've shown like 100 kilogram per day production, which is really impressive. Another question sort of along that line is, what kind of, on a plant design perspective, what kind of a load following capability can you have? Can you use intermittent electricity, that varies from half an hour to next half an hour? Can the plant, including all the auxiliary systems, do that without much storage?
Yeah, that's another great question, Ju. So, and there's multiple layers to your question. So can the electrolyzer itself have the applied voltage and the operating current upregulated and downregulated over significant swings? That we have tested. And in fact, we don't want to turn it off all the way to zero, but that's probably okay because you can keep some fairly modest reducing potential still applied. A little bit of current is sort of trickling through it. That actually keeps the system and the catalyst in good shape. And so I think I'm encouraged that the electrolyzer system itself will do well in terms of the load following. But then you mentioned all of the ancillary hardware, which is very significant. And we have a few more, compared to a water splitting electrolyzer, we have a few more degrees of freedom here, right? We've got our CO2 supply. We've got our purification apparatus at the outlet that could involve both liquid handling and gas handling. And so, we haven't explored the answer to your question on all of the ancillary systems. And yet we agree with you that it's going to be really important to do so. And then maybe just the final point I'll make on this is that there's another knock-on implication of this thinking, which is that our ambitions for capital cost reduction could be even greater than what I've put in here. The reason being that when you have all of these sort of interacting pieces of capital plant and you have intermittent electricity, you would love to be able to utilize the lowest cost electricity, but it may be only available for 12 hours of the day or 8 hours of the day, or on some days, 6 hours of the day. And so if we can make really big advances in the high activity, the high productivity, and therefore the lowering of the capital cost per ton product in these systems, then we can get into an even more attractive regime with respect to operating costs by using the lower price electricity. And so it just emphasizes how important your thought there is, Drew, about looking at the integrated system and its ability to handle renewable sources of power.
You mentioned that like 1 ampere per centimeter squared is like an industrial level of sort of, break even kind of current density. I wonder industrially, what level of operating stability for the catalyst, and how many, I think most of the academic papers are like a few hundred hours, but is that enough? And also, are there ways to regenerate the catalyst easily for long-term operation, and issues like a fouling or all different issues, coarsening? So how to maybe recycle the catalyst or reuse the catalyst?
Yeah, I'll take the second part of your question first. So the point about fouling is very interesting and very important, needs to be studied. We've started by studying it in one particular context, which is when you use CO2 that's not pure, but that might come from, let's say, a flue gas stream, and where most of the NOx and SOx would have been removed, but not all of it, right? You can imagine still having ppm of those constituents. What does that do to the catalyst and selectivity over time? And we have found that certainly at 100 ppm, you can start to lose selectivity on these copper catalysts after certainly 100 or so hours. So yeah, we've started to look at means to electrochemically regenerate in situ the catalyst. And we found that there's a number of strategies that are effective there. So that's encouraging. It clearly needs further study, but we're encouraged that it may be possible, to the extent that the catalysts become poisoned or fouled, that we may be able to reverse that process, and that it won't take us like half of our duty cycle to do it. It can take us 0.1% of our operating time to periodically regenerate the catalyst. So I'm encouraged on that front. And then with respect to your question about how long these things need to operate, here again, I agree with you. 100 to 200 hours is what we do in papers today. We're working towards some demos that are more like 1,000 hours. But in terms of sort of a credible initial commercial step, I would say that maybe 5,000 hours to get going could be okay if you've got a system that's very modular, and where in a cost-effective way you could potentially swap out a previous membrane electrode assembly and maybe regenerate or recycle that XC2 and then replace it with a cost-effective replacement membrane electrode assembly. Obviously, you'd like to further extend that beyond 5,000 hours so that you could reduce the operation and maintenance cost of your system. But I think 5,000 hours would be a very nice first milestone.
Thank you, Ted. There is a question from Zishuai Zhang. In your pilot plant, what are the OPEX, operating costs, and the capital cost per ton of ethylene?
Yeah, so roughly speaking, in systems where we project being able to make ethylene at about $800 a ton using renewable electricity, the OPEX and the CAPEX are roughly equally distributed. Slight majority OPEX, so let's call it $450 a ton, most of which is electricity cost, a little bit of which is operation and maintenance and materials, and then the capital cost makes up the balance of that number.
Okay, Stephen, maybe you just turn on camera and just ask. Yeah.
Good morning. Hey, Ted. Great talk. I'm curious. I like this idea of synergy, perhaps, between thermocatalysis and electrocatalysis. Could you talk about whether you're thinking about doing these things in parallel or in series? And if in series, which would be precursor to the other?
Yeah, well, I would say that first of all, that anything's in scope at the moment because it's early days. But I'll give an example of something that might be interesting, which is if we are trying to get to the C4 products, then being able to, say, take an electrocatalytic step from CO2 or CO to a C2 product, and then to do, say, an ethylene dimerization step in a very efficient way. But here's the critical point. Doing so directly consuming the unpurified outlet gas from the first stage. So the unpurified outlet gas from the first stage, obviously, I mean, you hope contains mostly ethylene, but in fact, it's going to contain from some CO or some CO2. It's going to have a little bit of hydrogen in it. It could have a few other components. And so being able to directly utilize that input, or conceivably, if there's some hydrogen or some CO chemistry that could actually be your ally and could allow you to increase the efficiency or let's say the robustness of the ethylene dimerization stage, that would be very appealing. So that's an example. So the answer to your question is that one's serial, obviously. It's tandem, it's integrated, and it's trying to achieve some kind of synergy that wouldn't be accomplished if these were two black boxes that were separated by a very high purity separation engine.
Okay, thank you, Ted, for this fantastic first